All right, so I think you'll be happily surprised about number 9 that you're asking about, because I just reminded myself of my notes, and it's one step. It's an easy one. You'll see. Don't worry about number 9. And like I said, we'll turn in that stuff at the end of the hour. So we're talking about the preferred choice, right, for bonding theory, and that's not valence bond, but there's an M.
Oh,
molecular orbital theory. Yep.
Valence is the oldest molecular orbital, is the most used, right? So that's great.
Yeah, it's kind of progressive. I'd say this one is much more quantum mechanically based. So that's where everything seems to be pointing right now.
Is that where that LUMO and HOMO
We'll be getting that. So the molecular orbital energy level diagrams is what they're kind of talking about here, and they're starting us out with this. Now, first off, yeah, we're talking about molecules, but not very complicated ones. Diatomic, that's how many atoms? 2. And then if you can really tell, but this is what type, so this would be H2. It's diatomic, but would that be heteronuclear or homonuclear? Homonuclear. Okay. So there's a lot of information in these diagrams. One is you take a look at hydrogen, and its electron configuration is just 1s1. So each hydrogen atom has a 1s orbital to contribute. So they list the atomic orbitals on the sides, right? In the center are your molecular orbitals. And a couple things that I like to see that they do right here is that they're consistent with, not really do it right, they're consistent with. Because sometimes we get lazy with our notation. This really is energy going up. And I like how this is one hydrogen atom's atomic orbitals listed on this side, another hydrogen atom's atomic orbitals listed on this side. They both have 1s. So they're both exactly at the same energy. Well, they should be because they're both 1s orbitals, right? So when we start mixing heteronuclear, don't be surprised when things get all, right? Because their energy levels are going to be different for the atomic orbitals that we're mixing. And what they're saying is you mix 2 atomic orbitals. Well, you get how many molecular orbitals then? 2. And there they are. There's a 1 sigma and a 2 sigma star. And if you'd like to see what they look like, we had diagrams of that last time. But essentially, now we have to put those 2 electrons in those 2 orbitals. Well, they both go in the bottom 1 sigma. Okay? And so those are some of the general ideas that you're going to see a lot. If we look at helium, so again, this is 1 helium atom. So they're trying to show you this molecule. First, did you ever hear that molecule before? No. Does it probably even exist? No, right? Because, I mean, first off, it's a noble gas. Noble gases shouldn't be forming diatomic molecules. But so here's their model. Helium has, right, 1s2. So now each one, again, has 1s orbital to mix. So that's why you see the 1s's here still. But now we've got, so you mix 1s orbitals. You get the same 2 molecular orbitals because it's the same linear combination of atomic orbitals. So you get the 1 sigma and the 2 sigma star. All right? And notice how, are they consistent with their star? What does the star mean again? Antibonding. So it should be higher in energy or lower in energy than the atomic orbitals you started out with. Should be higher. Is it higher?
Yes.
Yeah. So they're being consistent so far. I like it. So that's why it's anti-bonding. But there's sigma orbitals. You can only fit 2 electrons in there. So you have to put 1 in the bonding, 1 in the anti-bonding. Well, and then you can kind of tell by looking at it, I think, that you have just as much bonding character in the molecular orbitals as you do anti-bonding. So it's not going to exist. And we're going to, oh, that's right next. We're going to have an equation to actually characterize that. Now, again, this is all for diatomic molecules.
How do you tell the difference between the heteronuclear and homonuclear?
If we,
Oh, okay.
like if you did another one
Both homonuclear.
for CO, carbon monoxide, heteronuclear, right? So you'd have to list out all of carbon's atomic orbitals, oxygen's atomic orbitals. But they're really not going to be doing all of them. We're just going to be doing the valence electrons, because that's what's involved in the bonding anyway. Okay. So these are, so far, everything is homonuclear, diatomic. And we mentioned how He2 looks like there's just as much bonding as there is anti-bonding. Well, there should be a number to actually characterize this instead of saying it looks like there isn't any. And that's what bond order is. So you calculate your little b, right? 1/2 n minus n star. N and n star are probably what? What? Yeah, but number of what? What would make sense to put in there? Electrons. The number of electrons in the bonding and the number of electrons in the anti-bonding. So you get your bond order. And it's just like any idea when you think of bonds, if you have a bigger bond order, that bond should be shorter or longer? If I calculate a bigger bond order, would that bond be shorter or should it be longer? What would characterize that bond? Shorter, right? Yeah, and could we, it'd be stronger, it'd be shorter, it would be that whole idea.
Bigger bond order is shorter?
Does that make sense to you? Right? It should be, because we could be talking about multiple bonds. But what I like about it is that it's not 1, 2, 3, 4, 5. No, it's just a number that characterizes the bond. That we're overall bond order that we're getting in that diatomic molecule. Bond dissociation energy. Just the energy to break a bond, just like it. Not a whole lot to talk about that. Some of this is kind of redundant, but that's okay. There's kind of getting a little bit deeper into it, reminding us what a pi orbital is. So figure 1427 are examples of pi molecular orbitals. A couple of ways you can tell. One is you see the little pi symbol, right? But you have the overlap above and below the internuclear axis. And they're trying to say this is really the best way to think of a pi bond. Right? That it's cylindrical. I think that kind of makes sense because it wouldn't just be a cloud above and below.
Sorry. Sure. So the greater the bond order, the shorter the bond distance, and the stronger the bond.
Stronger the bond, the stiffer the bond, the higher the frequency of its vibrations. I mean, all that would follow. Overlap integral. I'd say something like a mathematical way to determine how much two atomic orbitals kind of like overlap. Right? It's the constructive interference idea. Right? If you take, for example, and they're going to give it the big, I think the book gives it the big symbol S, as an overlap integral. So it can almost look something like this, I guess. Right? Atom A, take its atomic orbital, and atom B have its atomic orbital, and you just integrate them. That's what integrals are, area, right? How much does this overlap? And then really you can get two extremes. For these overlap integrals, well, you could get 0. There's absolutely no overlap at all. And why is this important in the first place? Well, if you want there to be a bond, well, these integrals should be overlapping, and you should be getting some area, either above or below or in between the atoms. So atomic orbitals should be overlapping. So one extreme is just 0. There's absolutely no overlap. I don't know if you remember, we call that orthogonal. And then the other one would be the other extreme would be they overlap 100%. Okay. Well, let's finish this up first. This would be where they're identical, right? You'd have psi A star times psi A, two identical orbitals. Pretty much just a normalization condition, but okay.
When we're seeing orthogonal, we're talking about like two orbitals just 90 degrees from each other.
Well,
Perpendicular to each other?
orthogonal, in a typical way of thinking that I'm orthogonal to you, yeah, we're thinking that I have no component in my direction or my whatever we're talking about. I have no component that correlates with you. Or yeah, if I'm talking about physical position, I'm perpendicular to the wall or something. But orthogonal here more means like, I'd say this, that it's perfectly, the area perfectly adds up to be 0. There's absolutely no overlap of these two functions.
So the two densities are opposite.
So you have just as much area above, you have just as much positive area as you do negative area. That they just completely negate themselves, negate each other. So it's not really thinking of position so much as it is a mathematical calculation where you just get 0 for area. Okay, so this I'll be giving you. We just have to know how to use. Okay. So if you have these diatomic molecules, lithium, beryllium, right? These are the molecular orbital energy diagrams that we'll be using. All right, so if you wanted to actually make the diagram, it would look like this, right? And you list one atom on this side, you list the other atom on that side, just like they were doing up here. Okay. Except now we'll have more than one S to work with. Okay. So, for example, I think this is nitrogen. You have nitrogen there, because what is nitrogen? Now, this is all for valence electrons. So you pretty much just look at its noble gas core notation, right? Yeah, so just to be complete, 2s2, 2p3. Right, so this is the part you're looking at. So you notice how they just listed 2s, then they listed 2p, right? And each nitrogen has 5 valence electrons. That means 10 total we have to put in there. And when you do the center part, so this part, the outside 2 columns, you just kind of figure out from the valence configuration, right? And since they're both 2s and they're both 2p, it's homonuclear, they're going to be perfectly across from one another. If one was 1s, it'd have to be a lot lower, right? Just make sure you put it lower. But what molecular orbitals do you put in the center? You just get it from here. So nitrogen has how many valence electrons? 5. And we're talking about N2, so now we have 10. So you find something up here with 10 valence electrons. Now it'll be an N2, but the point is it's the number of valence electrons that really matter. What's the word for that? Let's see, how do I say that? If 2 diatomic molecules have the same number of valence electrons, what is that called? Like CO. How many valence electrons does carbon monoxide have? 4 and 6, so that would be a total of
And then
10. That would be 10 valence electrons. Okay, what up here, N2 has 10 valence electrons. So N2 and CO are, they have the same, I think the word, when we did this, we were talking about atoms. And this is how we did it. We weren't talking about molecules because we were just writing electron configurations of atoms. Let's see if you remember. And I said that O, or oxide, fluoride, Na+, all these ions formed because they are all isoelectronic with a what? Why don't we ever form Mg plus 1? Why is it always O minus 2? Why is it always F minus 1? All these ions, all these atomic ions, they had no choice in their charge. Transition metals kind of vary, but not these. All these were isoelectronic with a, how do we figure this out? Like, I look at nitrogen. Oh, I know that's nitride. It'll be N-3. What ion does carbon form? Carbide, C-4. I know that calcium is a +2. I'm always going back to what? Noble gases. Everything wanted the electronic configuration of a noble gas because that's extremely stable. So sulfide, S-2. Why? Because you give it 2 electrons, it has the exact same electron configuration as argon. Nitride, exact same electron configuration as neon. Okay, so nitride and neon are the I word. Iso? No! Isoelectronic.
Oh.
You don't remember that? Okay.
keep that in this class.
So that's isoelectronic. So what I'm trying to get across with all this spiel here is this column for nitrogen, for example, isn't just good for nitrogen. It's good for anything that is what with N2? Anything that is isoelectronic.
How would I describe that? It has the same.
Two things are isoelectronic if they have the same number of what electrons? Valence electrons. Right. Just like nitride and neon. Okay. So that's how you figure out what the center column is. I'm always going to be giving you something that's isoelectronic with this stuff. Otherwise, you wouldn't know what orbital to put in there. So it's nitrogen. In this case, it's N2 or something isoelectronic with N2. You just fill in the order of these orbitals, right? Notice how they have 1 sigma, 2 sigma star, 3 sigma, 1 pi, 2 pi star, and then 4 sigma star. And wherever there's a pi, there's actually, right? There's going to be, let's see here. Well, I kind of tell you over here. If you have, see, that's the order they filled them up here too. Okay. And you just have to realize that when you start with 2s atomic orbitals, right? Each one has 2s is how many orbitals? How many orbitals are in a 2s orbital? It's just 2s, so there's just one orbital. So one orbital, molecular orbital, you should only get 2 of them. That's why there's just 2 here. But if you have 2p, a 2p has how many orbitals really? 3, right? And if you're talking about atoms that are degenerate, right? But if you have 2p there and you have 2p here, man, now we're going to have how many molecular orbitals? 6. So count them up. We have 1, 2, 3, 4, 5, 6. So in these pies, there's really, that's why they're not, I wish they could draw it a little bit better, right? There's actually 2 orbitals, 2 molecular orbitals there. So pies are really 2 molecular orbitals. That's why you see whenever you see the pi, it gets maxed out when they have 4 in there. If you look up to like with O2, see how those 2 molecular orbitals, they're in different molecular orbitals. They're not paired. Okay.
Where?
Up here for oxygen,
They're not there.
right? There's 2 degenerate molecular orbitals there. That's why they kind of spread them out. Okay. So with this, you can kind of play around with things. And for example, if I compared F2 and F2 plus, which one would have a shorter bond? In other words, so if I compare F2 and F2 plus, what's the difference between the two in the first place? Yeah, one. I lost an electron in the F2 plus. So what you do is you write F2's molecular orbital energy diagram. You don't really have to write it because it's in the table, but if you did, you could write it. And then you look and see, okay, where am I pulling that electron from? Am I pulling it from anywhere? Which one is the outer? Is it going to be up here or down here? When you do this ionizing stuff, that's really what this is ionizing. Where do you pull these electrons from? What would be easiest? This is really energy. Because nature's going to do what's easiest. I'm not saying this is going to be easy, but you put enough energy in, you can do it. Would it be easier to pull out an inner electron? Yeah, the highest. You're going to pull out the highest energy valence electron. So if you remove this, how are you changing the bonding character? Are you removing a bonding or an anti-bonding electron? For this one, we're removing an anti-bonding electron. So if we remove an anti-bonding electron, F2 plus will have what type of bonding character in comparison to F2?
It would have 3 anti-bondings.
Yeah, so I mean overall, you can go through the work and calculate. Exactly. You can go through the work and calculate the bond order, but I don't think you have to. You just recognize that, oh, F2 plus has one less anti-bonding electron. So when I calculate the bond order, right, I'm going to calculate a stronger bond. Where did my bond order equation go? Here it is, right? This N star is going to go down by 1. And it should. Or you don't even really need to calculate it. Just think of it as, man, I'm removing anti-bonding characteristics. So that's going to make things even stronger, right? And if you're not comfortable with it, just go ahead and calculate B for F2, calculate B for F2 plus, and see that, oh, F2 plus is a bigger number. Okay. So that's the game that let's see if you're following this. What if I had N2 or N2 plus? Which one would have a shorter bond? Which one would be shorter? N2 or N2 plus? If you can even see this here. N2 plus have a shorter bond? You agree? Ricky, you agree with them?
I wish I knew how to do this. I don't know how to do this here.
Brad's right. Brad, explain it to him.
Let me guess. No, I'm kidding. I looked at the chart, figure 14.3, and I basically followed the same rationale that we did for the F2. We had 2 bonds. We knew that we're going to lose one bonding electron from the 3 sigma G. So then that would make it basically the same thing. You have an N2, which has balance throughout, and the N2 plus, which would be minus 1 electron. Is that adequate? Or
Yeah. Yeah. I look at it too. I blew this guy up because this is nitrogens. If you're going to make N2 plus, right? If this guy right here, if that star was not there, you'd be removing bonding character, and that's going to weaken everything. So it's just the opposite. You're removing anti-bonding character because you have to remove one of the highest energy electrons. So you're removing anti-bonding character.
That one, that top one isn't paired, right? Those are separate.
Yeah, they're separate, unpaired. Yeah, see here, they're kind of in order here, but not very good.
So what was the question? Whether N2 plus or N2 has a strong?
Has a shorter bond. What's the answer?
N2 has a shorter bond?
Which one has a shorter bond? Brad said the answer. N2 plus. Okay. Parity. Parity only makes sense if there's a center of inversion. If I have a molecule carbon monoxide or a molecule O2, one's homonuclear, one's heteronuclear. One of them has a center of inversion. Which one has a center of inversion? You can reflect through the center of that molecule and always get the same thing again. Which molecule? Oxygen or carbon monoxide? Oxygen, right? Because you can reflect. It actually has a center of inversion, and we're not drawing out this molecule, but I'm just saying it has to, right? So when you have a center of inversion, then they have parity, and that's why they have this little G and U, Gerade and Ungerade. It's got to be some German thing, I think. I'm not sure. So, and that's why a lot of these little molecular orbitals that you see, like see how this one says sigma G, right? This one says sigma U. So Gerade means the sign of the, remember the colors are supposed to be kind of the sign of the wave function. So it's not changing color. So that would be Gerade. Or you could have pi, right? These pi molecular orbitals. And if it doesn't change sign, it'll be Gerade, right? So this one would be Gerade, this would be Ungerade. So it only makes sense to have G's and U's on this stuff when it's homonuclear. If it's heteronuclear, you just got to get rid of these G's and U's. That's the only thing that changes, because there's no center of inversion anymore. You have the exact same molecular orbitals, just no center of inversion anymore, so no G's or U's. So I'm sure you'll see that in the coming up. It's like here, they wrote it in more general terms. There's no G's or U's there. Okay, so that would work for pretty much anything. So we mentioned what center of inversion. Heteronuclear diatomic molecules. Sure, you can get polar bonds. Polar bonds is because there was a difference in what? In the bond.
Well, because there was a difference in the sharing of the electrons.
Difference of the sharing. So what?
Share unequally.
Yeah, and there's a word for that. So it's an E.
Ionic, or electronegativity.
Electronegativity. Right. And there's a couple scales that they're going to use to calculate how polar a bond is. We're not going to worry about that. But partial negative, partial positive charges, right, all due to electronegativity.
But the partial is the same as diatomic.
If
When we say something is
all right, this is what it kind of means, right?
okay, that's possible.
I remember that book in electronegativity from Spartan.
Yeah.
Had the units in there.
So we I'm not going to really dig into any of those, but the
Good to see.
the last, I think, concept here that the book wanted to get out of this chapter is this idea called the variation principle, where, let me write the Schrödinger equation here. So the Schrödinger equation is supposed to be really hard to solve. So you mentioned the Spartan. So what's going to happen is you just throw this molecule together in Spartan, and it throws a bunch of atomic orbitals together. The more atomic orbitals it uses, actually the better, but then it gets even uglier and takes longer to calculate. But what it's going to do is it'll apply the Hamiltonian operator to your trial wave function. Just throw something together. You don't know if it's the right answer or not. And then you get some energy. And then you get the wave function back again. Okay. That energy you're never going to nail and get the exact right energy, because that means that wave function had to have been right. Well, that'd be an awfully good guess. So, but more than often than not, almost always, it never is. So that means that energy is going to, here, let's see if you get a feeling for this. It calculates these trial energies. They're always going to be too high or too low. What would be your guess?
Different isotopes and
Well, you're trying to calculate anything you did in Spartan. You're trying to calculate geometry. You're trying to calculate ionization energies. You're trying to calculate vibrational frequencies. You're trying anything, polarity, right? Because the wave function will give you all that information. Well, let's just talk about one thing, and let's talk about the energy of that molecule. Maybe it's ionization energy or something like that. So it just makes its best guess at a wave function, applies the Hamiltonian operator, calculates an energy. More than likely that energy is going to be too what? High or low? If it's off. If it's off, it's going to be too high. Right? Because remember, low is great. So if it was doing great, yeah, it'll be low. So it's always going to be too high. This energy is always going to be too high than the true. So then it modifies the wave function again. I'm even worse. It modifies the wave function back, keeps modifying that wave function, and does it really, really fast until it minimizes those energies. So,
Yeah, so its guess is going to be higher than the actual.
yeah, the result.
Okay.
The result. It's guessing at the wave function, and then it calculates the energy, which is almost always too high. So the idea here, the real goal of all this, is to get I don't know how you draw it, a potential energy surface is the real goal. Because that's the part of the Hamiltonian operator that, right? Remember it had a kinetic energy part and a potential energy part. So if you can get this potential energy surface down, and it's this hills and valleys, and where it's going down really low is where, there's our minimum energy. That's where our true answers are found. But as you move the atoms around in the molecule, what's the resultant energy? Okay, if you want to talk about vibrations. So that's kind of really what's going on here. Is they're really after this potential energy surface, and basis that's that trial wave function. If you remember, they started out saying something like, right, or those were your atomic orbitals, and Ci was the weight. So very often that's your basis set. And the more atomic orbitals you use, man, the better off you're supposed to be, but things are going to get even uglier. And then they get into terms like dimension, and I think this is going a little more, now we're getting a little deeper than we even need to go. So we'll just kind of leave it. Okay. So just want to get started on some homework, and I want to talk about that number 9 that you wanted to see. So if we go back, number 9, hint page 388. What is page 388? So we're all- Well, I don't know. Okay. So if it's mutually orthogonal, that means that we're trying to see if this integral is actually 0. Right? And they're kind of lazy here. They're trying to say that, okay, here's one function, and then here's another function, and show that they're orthogonal. Okay. So what we need to do is just put our wave functions in here. Okay. I want to call it 1 and 2 or something. So maybe that would be that'd be one of our wave functions. And this would be another one of our wave functions. It really doesn't matter which is which because they didn't. Okay. So we just put them in. Okay. But like most of these problems, the hardest part is trying to figure out why we set it up the way we set it up. Okay. So first off, maybe that's where the hint page 388 was about, just to give it a little reading in that if you want to talk about orthogonality, we're talking about, oh man, that's an extreme for these overlap integrals. Extremes are either 0 and 1. And orthogonality is one of those extremes. But the point is that they're talking about these overlap integrals. And that's where you take you take the integral of the two and multiply them together and integrate it. Okay, so, and I put 0 here because they say, just show that they're mutually orthogonal. So, and I put a question mark above to show that, well, we're just verify it. Okay, so that's why it's set up the way it is. So if you want to see if anything is mutually orthogonal, it just means that you have to have an integral, and you have to be multiplying two wave functions together. So the confusing part is maybe also up here, where are the two wave functions? Well, that's what the plus minus thing is. There's one wave function is a plus, the other one is a minus. Okay.
Yeah, that can be confusing.
Yeah. But now you've seen it, so now it's super clear. So now we have to finish this. So what would you do? Distribute, yeah. So we could have just multiply the a through and then do the b through, right? And make it a whole bunch of different integrals. It looks easier that way.
So you get y squared plus 2
I'm just doing the a through. Oh, I forgot my complex conjugate. Look at that. I went from here. I didn't do my complex conjugate, did I? Forgot about that, right? So this is really
Why does that need to be there again?
because of our starting point. It's always complex conjugate, right? It's always complex conjugate. So I guess this is my starting point. It's kind of like when we said, oh, if there's a normalization problem, you should have a starting point. You gotta know what that initial starting point equation is. So for orthogonality, really the starting point is S. Big S equals these integrals. And then, well, they could, to what degree do these wave functions or these atomic orbitals, whatever we're referring to what degree do they overlap? Well, you calculate it. In this case, it's supposed to be an extreme because they're supposed to be orthogonal, so we wrote 0.
I have a question. So when we set up this complex conjugate, much like we did with the other ones, we did an A variant and a subtraction variant. Do we do an addition and a subtraction for each one of those? So does this become the wave function A as star plus the wave function B as star times all that? And do we multiply it by itself again, but now we do a negative and a positive?
No. They're trying to say, so starting over again, this is our starting point, overlap integral. Okay, so what is your S? Your S, you're supposed to show that it ends up to be 0. So to me, the really confusing part here is, in this question, 14.9, they had to have told you what two different wave functions here. What two wave functions am I supposed to calculate the overlap integral for? And you got to get it out of that question, and that's what you put in for those two wave functions. And what they did is they put it in a shorthand notation way, kind of a lazy way, right? Where they said one wave function is plus, the other one is minus. And that's also what they're trying to illustrate on page 388, that only one combination really gives you a... Only if, on page 388, it's the exact same thing. That's my starting point. But on page 388, only the plus gives positive results. I can just write the A, right? I'm just going to copy this. Well, I'll copy it exactly. Psi S A. Right? Only the wave function where only the plus combination is going to give you a non-zero overlap, according to page 388. They both have to be plus. If you have them both be minus, nope. And we can do the math to show it. If one is plus, one is minus, again, everything's not being orthogonal. So that's, in this question, 14.9, they wanted us to pick one of those combinations. So in these overlap integrals, right, they're saying that do the plus and the minus combination, right? That the bonding and the anti-bonding combinations are mutually orthogonal.
If you said they were both plus or minus, what would happen?
Try it. Well, let's do this one first. One step at a time, right? So great question. Just try it. But first, let's show you how to do one of these. Okay. So we're doing the plus and the minus combination. We could do the plus and the plus. We could do the minus and the minus, right? Whatever combination we want, and find out the overlap integral. They want us to do the plus and the minus. Fine. So this is how it starts out. Here's the plus and the minus combination. Remember, the first one is always complex conjugate. Because why? That's how you do overlap integrals, right? Okay. So we have to distribute our complex conjugate. And then we'll do this will be my first term, right? Just multiplying the psi A complex conjugate through. Second term minus, well, that'd be minus, right?
Yes.
There's my second term. Hang on, not quite. Psi A star. What's my next term? Well, it should be minus psi B. have to do multiply through my psi b through, right? Okay, so does this make sense so far? Just multiplied everything through. Okay, now there's another assumption here, but I guess you got to get that from the reading, page 388. These are supposed to be, for example, like atomic orbitals, and they're not picking any atomic orbitals. They're picking those mutually orthogonal atomic orbitals. In other words, if you remember the talk about that, if you pick it makes the math so much easier for these computers and for us if we can do it by hand. What will this integral be? If it's normalized, and they are, they didn't just pick junky. What will this first integral be? Psi a star psi a. That would have to be what number? Doesn't this perfectly fit the what condition? If it's normalized, it has to be what? It has to be 1. So let's just put an arrow through it or something and write a 1 on there. This has to be 1. Okay, do we have any other ones that we could? Yeah, the very last one. There's another one. Okay. Now, if we have to go, I would say if you go back up into the beginning of maybe even the very first day when we're picking these out, we were talking about how this linear combination of atomic orbitals, you can pick all these atomic orbitals, but they're mutually orthogonal. If you pick any two of these atomic orbitals and try to integrate them, but they make them different, you always get what? They're all mutually orthogonal. They have to be.
If they're orthogonal, they're not orthogonal.
Where did we talk about that? Oh, I may not find it. Here's kind of where we talked about it, but we didn't really see it. If I take a, they're different. Mutually orthogonal. It has to be 0. They're different. So
+1 and -1.
this one would be 0. This one would be. So what do we end up with?
1 minus 1.
1 minus 1, which is
0.
0. Okay. So you could try this again with, right, making psi 1 be the plus combination, making psi 2 be the plus combination, and see what you get. Having psi 1 be the minus combination, having psi 2 be the minus combination, see what you get. And that's what page 388 did. And they didn't show you all that, but page 388 said, oh, there's only one combination that gives a non-zero overlap, and that's the plus combination. So that could be another homework question. Good test question. Good test question. Right?
I'm sorry.
There should only be 4 terms. What did I do here? I did one twice. I did this one twice. See, look at that. I did this one twice. Yeah, there's only 4 terms. You distribute psi a star, then you distribute psi b star. There's only 4 terms. Okay.